And like Cornejo said, you have started taking tabs on him at 0 itself. He's already got a -4 velocity at 0, so you have to include the 0. It's not like he's not moving there. He is moving there this time, right? Because he's already moving, and you start to take tabs on him. That's when the time started. Now, what if you didn't have the beautiful picture I just drew? Most of you won't. Your picture won't be as beautiful as mine. So we don't have this beautiful picture. How are you going to find the answer to moving right and moving left?
You find where the x-intercepts at.
As an equation. Or an inequality. You would simply set 2t minus 4, right? That's velocity, greater than 0. You're going to solve these little inequalities. Okay? So here, how does it read? If you proceed through this, 2t greater than 4, t greater than 2. Well, that's what it's already said, t greater than 2. The difference is, in this particular problem, we have to truncate it at 5 just because of the nature of the interval they gave us, right? So we have to stop at 5. So the inequality cannot give you the stopping point necessarily, right? You have to watch for the original interval. So too for this one, if you want to know when it's moving left, when is v less than 0, same basic inequality, we would solve 2t minus 4 less than 0. Same basic algebra. 2t less than 4, t less than 2. But ours has to stop at 0. Can't go any less than 0 in this problem, right? Part C. Determine the velocity and acceleration of the object at t equals 1. Determine velocity and acceleration at t equals 1. It's no big deal. We have the velocity function already, right? 2t minus 4. So all I need to do is plug in 1 into the v function. So 2, 1 minus 4 is negative 2. Is that right? Okay, let's on that, it's okay. You just started to scare me. So what does that mean? It means over here 1, you should have a velocity of negative 2. So on the red curve, that would be right there. Right? 1, negative 2. That's about right. Not that bad. Okay. So what are the units, though? It's a velocity. So it's the original s units over the original t units. So feet per second. Right? S is feet, t is seconds. So feet per second in this problem. You need to know the acceleration at 1. How rapidly is the velocity changing? That's what acceleration is, right? How is the velocity changing with time? So we need to take the second derivative. We already have the first over there, so let's take the second derivative. Acceleration is the first derivative of v, which is the same as the second derivative of s, right? Just going down the chain. So the first derivative of v over there is just 2. It's a constant. So whenever you plug in 1 for t, there's nowhere to plug anything, so the answer is always 2. Right? His acceleration is constant. It's always 2 feet per second, squared. Right? That's how his velocity is changing always. 2 feet per second squared. Determine the acceleration of the object when its velocity is 0. Okay. A little more convoluted. Determine velocity determine acceleration of object when velocity is 0. Yeah. Okay?
It's going to be 2.
Yeah, it's always 2.
So is that
agreed? It's constant, no matter what you put in there. Now, let's say it wasn't constant. What would you have to do? Plug in the time. What's the time when the velocity is 0? What's the time when velocity is 0? 2. I would take 2 and plug it into the acceleration function, correct? That's what we had to do. This time it's always the same, so it's no big deal. It's always 2 feet per second squared. Any questions about position, velocity, acceleration problem? Straightforward enough? Next one. Growth models. What I find is, first, an average growth of said function. So I think the book uses P of t for the growth model. Come on for population. Just quickly here, the notation is. Yeah, P of t. Huh? That one. So P is the population of something objects at time t.
Population of objects?
Yeah, something, whatever it is. Could be squirrels, penguins, anything. Here's your question. Are penguins mammals or birds? How do you know?
Mammals if they lay eggs. Yeah, they lay eggs.
So is platypus.
But they can't
So is
fly, so they
platypus.
can't be heard.
Platypus.
What's
They
the
can swim.
definition of a mammal?
The back can fly, it's not a bird.
They can swim.
What can swim?
It's a penguin, right?
So do ducks.
Yeah.
Alright.
They both lay eggs. Look, they both lay eggs, right?
So,
But they don't.
so do frogs. Carrie, what's the answer?
Well, according to this,
Ducks can fly.
mammals are amphibians because they live in water, on land, or both. Penguins are birds even though they spend time on land and in water. So it sounds like it's all of the above.
It's a bird. It's the awesomest bird in town.
A bird that can swim underwater.
They can't fly.
What?
There's a
I think
lot
it's
of
the only
birds
bird that can't fly.
Is the penguin the only bird that can't fly?
I think about that.
Huh? I can think of 10 off my top of my head.
Chickens can't
Penguins.
fly.
Chicken.
They can't. They can't swim.
Oh yeah.
Can they?
Can't dive.
Chickens?
Oh yeah.
Ostrich, classic case, right? Ostrich don't fly.
They can dive.
They're too
They
heavy.
can what?
What?
What's too heavy? Ostrich?
Yeah.
Oh, it's nice. His little wings are too small.
No, but they're not.
What about roadrunner? Roadrunners don't fly.
They run.
They run, that's right.
So-
They're not called road flyers. Right? All right. The name tells it all.
Isn't a road runner the same thing as an ostrich?
I don't think so.
Yeah.
No. Oh, you're thinking of the cartoon. Because the roadrunner always puts his head in a hole.
They look exactly like an ostrich.
Really? You're thinking in real life?
No, they look nothing like an ostrich.
No. Looks like a really skinny bird, right?
Like what's it called?
like
In the
silent
cartoon,
chicken.
it looks like a.
An ostrich.